Hello everyone, I am Nitesh. I'm a PhD student at University of Wisconsin-Madison. I will be presenting our work on magnetoelastic instability induced pattern transitions in soft ferromagnetic laminates. Magnetoactive elastomers belong to a class of soft active materials that respond to the application of magnetic field. In principle, they consist of magnetizable particles that are embedded in the soft matrix. In the presence of magnetic field, the particles interact with the field and also with each other. Because of this magnetomechanical coupling, the properties of the MAE can be modified remotely and reversibly, and also they can be deformed by the applied magnetic field. The magnetic field induced variation in mechanical properties can be used for suppressing vibrations and noise, and the field induced deformation can be used for designing actuators. However, the strain levels generated in these materials are very small, of around 1%. This limits their potential use in soft robotics or as artificial muscles. On the other hand, the elastic modulus of the MAE can be varied up to 200%. We will show that how we can harness this capability of MAEs in an unconventional way to increase its range of applications. Here we propose the use of MAEs to tune the instability development in architectured materials. The development of instability depends on the two factors. The first is the microstructure geometry, and the second is material properties. Now, if the material is magnetoactive, we can tune its behavior by applying the magnetic field, thereby tuning its instability characteristics. Instability in architectured materials lead to sudden microstructure transformations, and that can be used for switchable functionalities. For example, deformation controlled acoustic metamaterials with band caps in soft robotics, designing tunable optical materials, and tunable auxiliary behavior. In our study, we consider a layered composite. It consists of periodic arrangement of stiff and soft incompressible layers. When the composite is compressed along the lamination direction as defined by this deformation gradient, the stiff layers undergo buckling, leading to a new microstructure patterning. In our study, we consider the layers to be magnetically active, and we study how its buckling behavior change in the presence of magnetic field that is applied perpendicular to the layers. We started with experiments on a single layer. The specimen consists of magnetoactive layers sandwiched within a soft matrix, and it is compressed horizontally along the layers in the presence of vertical magnetic field. Here we show the array of experimental images of specimen under combined magnetic and mechanical loading. Horizontally, the compressive strain increases from left to right, or the stretch decreases. Vertically, the magnetic field increases from 0 to 1.8 Tesla as we go from bottom to top. From these results, we can clearly see that the buckling amplitude increases with the application of magnetic field, or in other words, the instability develops at higher values of stretch. As we can see, at stretch equal to 0.92, there is no buckling when there is no magnetic field, but at 1.8 Tesla, there appears to be some wavy pattern. Motivated by the experimental results, we analyze this system analytically. We use the periodic unit cell to model the response of MAE. The constitutive behavior of both the phases is defined using an amended energy function that is a sum of elastic and magnetic part. We consider the elastic part to be defined by New-Hawkian hyperelastic model, and the magnetic part consists of magnetic free energy of material and the second term, which is basically the magnetic energy in vacuum. Since here we are modeling the ferromagnetic behavior, we chose the Langevin model to define the magnetic free energy that can capture the saturation effects at higher magnetic fields. This model has two parameters, susceptibility and the saturation magnetization. Let's look at the magnetic behavior of this model. From the magnetic energy, we evaluate the magnetization, which is a function of magnetic field B. From the plot, we can see that when the magnetic saturation is infinite, the magnetization increases linearly with the magnetic field. However, for smaller values of saturation, we can see a nonlinear response, and the curves approach the saturation values at larger magnetic fields. like the red curve approach the value of 2. Next, we will look at the method used to predict the onset of instabilities. The instability analysis is performed in two steps. First, we deform the MAE quasi-statically in the presence of magnetic field as per the deformation gradient F. The balance of linear momentum gives us the equilibrium condition in terms of the first Piola-Kirchhoff stress tensor, which is defined using the energy function which we saw earlier. Additionally, we have governing equations for the magnetic field. Here the naught superscript is used to denote the fields in the reference configuration, and they can be related to ones in current configuration like this. Next, we perform the Bloch-Floquet analysis superimposed on the finite deformation. In particular, we perform the incremental linear analysis with the assumption that these incremental quantities are sufficiently small. To this set of incremental governing equations, we seek the incremental field solutions in this form. Basically, they represent the potential bifurcation solutions with characteristic Bloch wave number. Moreover, the incremental fields also satisfy the quasi-periodicity condition along the E2 direction, which is defined in terms of the Floquet parameter K2. Now, if this bifurcation solution is possible, then after clubbing all these equations together and with some manipulation, everything boils down to this eigenvalue problem. Note that the matrix K is a function of material parameters, loading variables, stretch and magnetic field, and the Bloch wave number. Hence, the instability occurs when the absolute of eigenvalue of matrix K is unity and the corresponding variables are termed as critical variables. On the basis of value of K1 for which the condition is satisfied, the instability can be classified into two types. First is the macroscopic or long wave instability with wave number almost equal to 0, which means that the wavelength is significantly larger than the microstructure. And when the wave number has finite value, then it is classified as microscopic instability. In this case, the wavelength is of the order of the microstructure. Furthermore, on the basis of Floquet parameter K2, we get two distinct buckling modes. When K2 is equal to pi, we have antisymmetric mode, and for K2 equal to 2 pi, we get the symmetric mode. Out of these two, symmetric mode is commonly observed, whereas antisymmetric is very rare in layered composites. First, let us consider the laminate with smaller volume fraction of active layer, that is 0.05. This plot shows the critical stretch versus the applied magnetic field. Clearly, the critical stretch increases with the field, agreeing with what we saw in experiments. Now, let's look at the change in the critical wave numbers. We can see that wave number K1, which defines the buckling wavelength, is non-zero at smaller magnetic fields. With increase in magnetic field, it decreases and gets 0. Therefore, initially we have microscopic instability, and at higher fields we have long wave instability. And K2, which defines the Floquet periodicity, is equal to 2 pi. Therefore, it is a symmetric buckling mode. Now consider the laminates, which majorly consist of active layer. Here also the critical stretch increases with magnetic field, but we see a different behavior in the variation of instability modes. For these laminates, we get 0 wave number at smaller fields, which transition to microscopic instability at higher fields. Also, the Floquet periodicity is pi, therefore this is a antisymmetric buckling mode. Here I have covered only a few of the results. For more details, please see our paper. In summary, we observed in our experiments that the occurrence of buckling in laminates can be controlled remotely by the applied magnetic field. As a result, we can tune the amplitude of the instability patterns. Furthermore, we analyzed the instability development in laminates theoretically. Through our analysis, we found that there are multiple modes of instability in the magnetoactive laminates that are not even possible in a purely mechanical setting. Also, we identify the key parameters to switch between these buckling modes. Thank you.